In the silence of the cosmos, a single star burns. From afar it appears eternal, a steadfast beacon in the infinite sea of night. For ancient eyes, it was a guide, a fixed point by which journeys could be measured, destinies charted. Yet beneath its glow lies a truth more fragile. No star is eternal. Each carries within itself a fate it cannot escape. Stars live by the balance of forces, gravity pulling inward, fusion pressing outward. But balance is not forever. Sooner or later, gravity wins. The core collapses. Matter is crushed to densities beyond comprehension. And here, at this threshold, reality itself hesitates. One path leads to silence, a black hole, a pit where even light is bound in darkness, and time itself bends beyond return. Another path leads to endurance, a neutron star, no larger than a city, yet so dense that a single spoonful outweighs a mountain, still pulsing against the dark. But what if both fates are true? What if, at the moment of collapse, a star does not choose, but divides? What if one death becomes two, one reality swallowed in infinite night, another trembling faintly as a pulse in the void? Quantum mechanics whispers that reality is not singular, but branching, that in the smallest scales, outcomes are not chosen, but multiplied. And if this is true for particles, why not for stars? The cosmos may be a mirror fractured, every collapse a choice that is never truly made, every death a story told twice. And so the question lingers, heavy and unanswerable, when the stars split into two realities, which one are we living in? The night sky has always been a stage for wonder, long before telescopes and equations, long before even the concept of science itself. Human beings raised their eyes to the scattered fires of heaven and asked what they were. To the ancients, stars were eternal. They were the fixed lights, the unchanging backdrop against which the fleeting events of life unfolded. They guided migrations, seasons, and myths. Constellations became stories of gods and heroes. Their brilliance was a reminder of permanence in a world of change. Yet even then, hidden in myth, there were whispers of impermanence. In Hindu cosmology, stars were sparks of divine fire, destined to extinguish in the endless cycle of rebirth. The Stoics imagined ekpyrosis, a great cosmic conflagration in which stars would all dissolve back into primal fire. In Norse sagas, the twilight of the gods was written in the fading of stars. To many, the heavens were not eternal, but actors in a drama that ended, inevitably, in death. Humanity sensed, without knowing, that stars carried mortality. The first scientific cracks in the illusion of eternity came much later. By the 17th century, Johannes Kepler studied the heavens, not through myth but through mathematics. He saw planetary motion as part of a divine geometry, a kind of cosmic music in which stars and planets participated. Yet still, stars were thought of as permanent. They were the candles of heaven, consuming no fuel. Never dimming, it would take the 19th and early 20th centuries for the illusion to collapse completely. As the science of thermodynamics grew, physicists realized that no system could burn forever. Every flame consumes its fuel. Every engine exhausts its heat. Stars too must obey this law. But what fuel could they possibly burn? It was not coal, nor oil, nor any chemical fire. Their power was too immense. The answer arrived with nuclear physics. In 1920, the British astrophysicist Arthur Eddington proposed that stars shine because hydrogen atoms fuse into helium, releasing vast amounts of energy. A star's life, then, was not eternal but finite. The balance of fuel against gravity. When the fuel ended, gravity would prevail. Here begins the true story of stellar fate. For in the crushing grip of collapse, reality bends toward extremes. Stars do not die gently. They collapse into forms stranger and denser than imagination had once allowed. In the 1930s, a young Indian physicist, Subramanian Chandra, made a discovery that would forever alter astrophysics. At just 19 years old, while traveling by ship from India to England, he calculated the limits of stellar corpses. He showed that white dwarfs, the faint remnants left when small stars burn out, could only exist below a certain mass, above roughly 1.4 times the mass of our Sun. Gravity would overwhelm electron pressure, the very force keeping the star from collapse. No white dwarf could survive beyond this threshold. It was a revelation that bordered on heresy. For if not a white dwarf, what then? The star must collapse into something else, something beyond known physics. When Chandrasekhar presented his work in London, the great physicist Arthur Eddington dismissed it publicly as absurd. Eddington could not accept that nature allowed such catastrophic collapse. Yet history would prove Chandrasekhar correct. He had uncovered a boundary in the fabric of stellar fate, a point of no return, where stars must seek new forms. The first of these forms was glimpsed decades later. In 1967, Jocelyn Bell Burnell, then a graduate student at Cambridge, noticed an odd, repeating signal on her radio telescope records, a pulse, arriving every 1.3 seconds. At first it was so regular that she wondered if it could be artificial. Her team jokingly called it LGM1, short for Little Green Men, but it was no alien signal. It was the heartbeat of a neutron star, the collapsed core of a massive star. Its matter compressed into nuclear density, rotating with unimaginable precision. A neutron star is matter at its most extreme. The size of a city, yet with more mass than the Sun, it is so dense that 1 teaspoon weighs billions of tons. Its crust is a lattice of neutrons harder than steel. Its magnetic field a trillion times stronger than Earth's. In their discovery, Bell Burnell and her colleagues revealed that death did not mean silence. It meant transformation into a pulsar, a lighthouse of the cosmos. But neutron stars were not the only fate. Another possibility had lurked in theory since the time of Einstein. In 1915, Karl Schwarzschild, solving Einstein's equations of relativity from the trenches of World War I, described a collapse so complete that space-time itself would curve into a singularity, a point of infinite density, cloaked in an event horizon. This was the black hole. For decades, black holes were mathematical curiosities, solutions too strange to be real. But in the 1970s, astronomers studying X-ray emissions from binary star systems began to find candidates. One object in Cygnus, invisible yet pulling on a companion star, revealed itself to be too massive and compact for anything else. It was a black hole, swallowing light and time. Thus two fates emerged from theory and observation, the neutron star and the black hole. One pulsates, broadcasting its existence in radio waves and X-rays. The other vanishes, hiding its singularity behind an unseeable veil. Both are born from the same process, the collapse of a massive star. And yet their distinction lies on a knife's edge of mass and physics. To light, and the collapse halts at a neutron star, too heavy, and no force in the universe can resist the fall into a black hole. This boundary is fragile, delicate, uncertain. Observations show neutron stars with masses up to about 2 suns. Black holes, curiously, seem to begin at 5 suns or more. Between them lies a mystery, a mass gap where almost no objects are found. Why the silence? Why do stars not leave corpses in this range? The gap hints that the laws of collapse may not be simple, that reality itself hesitates at the threshold, and here the story turns toward speculation. For what if collapse does not always yield one fate alone? What if, at the moment of stellar death, the universe itself divides? A star teetering at the edge might become a neutron star in one reality, a black hole in another. Both outcomes, equally possible, equally real. This speculation is not merely poetry. At the smaller scales, quantum mechanics insists that outcomes do not collapse until measured. Particles exist in superpositions, both here and there. Both spin up and spin down until reality chooses or branches. The many worlds interpretation of quantum physics dares to suggest that reality never chooses at all, that every possible outcome is realized in some branch of the cosmos. If this is true, why would it not apply to the grander scales, to stars themselves? Thus we return to the paradox: a single star, one moment of collapse, 2 fates unfolding. In one universe, a pulsar spins eternally, its beams sweeping like cosmic metronomes. In another, a black hole waits in silence, erasing even the memory of the star that was. From Chandrasekhar's equations to Bell Burnell's pull, from Schwarzschild's singularity to Cygnus X1. The evidence accumulates. Stars carry more than one destiny. Their ends may be written not in certainty, but in multiplicity. The discovery phase of this mystery closes not in clarity, but in tension. Humanity has learned that stars are mortal, that their deaths give birth to remnants stranger than myth ever imagined. But with each discovery comes a deeper unease. The laws of physics do not guarantee a single fate. They suggest a fragile threshold, a border where reality itself may branch, and so the foundation is set. The ancients saw eternity in the stars. Science has revealed their mortality. And now the frontier deepens, for in their deaths, stars may not vanish into one truth, but fracture into 2. There is a moment in science when knowledge, once thought secure, cracks beneath the weight of discovery. For astrophysics, that moment arrived when the clean mathematics of stellar fate collided with the messinzas of reality. The death of stars, once believed to follow inevitable paths, instead revealed fractures, paradoxes, and contradictions that no single theory could resolve. At the heart of the shock lies a question deceptively simple: what happens when a massive star collapses? For decades, physicists assumed the answer was singular. If the star was heavy enough, it became a black hole. If not, it became a neutron star. A binary choice, a cosmic either-or. Yet as observations deepened and calculations refined, cracks emerged in the certainty. One such crack is known as the mass gap. Neutron stars have been measured with masses up to about 2.1 times that of the Sun. Black holes, detected through X-ray binaries and later through gravitational waves, appear no lighter than about 5 suns. Between them lies an empty range, a desert of possibilities. Why should nature avoid this band? Is it a flaw of observation, or is there something profound hidden in the silence? This gap unsettled astrophysicists because it hinted at more than observational bias. The mathematics of collapse, governed by Einstein's general relativity, allows for smooth transitions. A star heavier than the neutron star limit should collapse into a black hole without hesitation. Yet reality seems hesitant, skipping over the gap as though nature cannot decide. It is as if collapse at this threshold is unstable, a coin balanced on its edge. Then came the discovery of gravitational waves, ripples in space-time itself. Predicted by Einstein in 1916, but detected only in 2015 by the Laser Interferometer Gravitational Wave Observatory. LIGO, these faint signals revealed collisions of black holes, their masses measured through the vibrations of space-time. To astonishment, some of these black holes were lighter than expected, brushing close to the mass gap. Others were heavier than any neutron star should be, yet not heavy enough for black holes predicted by standard stellar evolution. The clean binary of outcomes was broken. The paradox deepened in 2017, when the event known as GW 170817 shook astronomy. Two neutron stars collided, sending gravitational waves across the cosmos and producing a burst of light observed in every wavelength. For the first time, the universe revealed both gravitational and electromagnetic signals from a single cataclysm. In the aftermath, models suggested the remnant may not have chosen immediately between neutron star and black hole. For precious seconds, perhaps minutes, it may have straddled both fates, a hypermassive neutron star spinning at breakneck speed, collapsing at last into a black hole. Here lay the unsettling truth. The line between neutron star and black hole was no line at all. It was a fog, a liminal zone where equations falter. In that fog, the fate of a star is neither one nor the other until conditions tip it across an invisible threshold. To quantum physicists, this language was hauntingly familiar. It echoed the superposition of states, the strange truth that, at microscopic scales, reality does not decide until it must. Could the death of a star be quantum in nature? Could an object weighing more than the sun, spanning tens of kilometers, exist in superposition, both a neutron star and a black hole at once? Such a notion seemed absurd. Quantum effects belong to the microscopic world of atoms and particles, not two giants of nuclear matter. Yet the equations of collapse did not rule it out. In fact, some physicists began to wonder whether stellar death could be the largest stage where quantum uncertainty plays out. This speculation struck at the foundations of physics. General relativity describes gravity with seamless precision at cosmic scales, bending light, guiding planets, and curving spacetime around stars. Quantum mechanics governs the microscopic, where particles appear, vanish, and interfere like waves. The two theories are pillars of modern science, yet they refuse to reconcile. Nowhere is their conflict sharper than in black holes, where relativity predicts infinite density while quantum physics insists that infinities cannot exist. The collapse of stars, therefore, is not just an astronomical drama, but a crucible where the deepest contradictions of physics converge. A neutron star presses matter into nuclear density, where neutrons are packed like bricks in an impossible war. Push further, and relativity declares collapse unstoppable, while quantum theory demands resistance. Between these forces, certainty dissolves. This is the scientific shock, the realization that stellar death is not merely astrophysical, but ontological. It asks whether the universe must decide one outcome, or whether, in truth, both outcomes exist. Some physicists look to the many worlds interpretation of quantum mechanics, which posits that every quantum choice splits reality. Apply this to stars, and the picture is staggering. At the moment of collapse, the universe itself may branch. In one branch, the star stabilizes as a neutron star. In another, it falls into a black hole. Each reality continues, independent, unaware of the other. The star has split not into remnants, but into worlds. Others resist such speculation, preferring astrophysical explanations. Perhaps the mass gap is an illusion, a result of incomplete data. Perhaps supernova explosions, the violent deaths that trigger collapse, are not uniform. Slight differences in rotation, magnetic fields, or composition could steer outcomes away from the gap. Yet even these explanations admit uncertainty. The fate of stars may be determined by chance, by turbulence, by chaos, and if chance rules, then the death of a star is not written in destiny but in probability. It becomes a cosmic roll of dice, a collapse balanced on the razor's edge of physics. There is another layer to the shock, darker and more profound. If black holes and neutron stars are linked by uncertainty, then what of information? The black hole information paradox, proposed by Stephen Hawking, suggests that information swallowed by a black hole may be lost forever, violating quantum law. But if a star at death can hesitate between neutron star and black hole, then perhaps information is not lost, but branched. In one reality, it radiates outward in pulsar beams. In another, it vanishes behind an event horizon. Both true, both false, depending on where one stands. For astronomers, these questions are not abstract. They are written in data, in light curves, in gravitational waveforms arriving at Earth. Yet the deeper they look, the more elusive the answers become. Each observation adds weight to the paradox. The universe, it seems, refuses to give a singular story, and so the shock lingers that stars, symbols of constancy for millennia, dissolve at their end into uncertainty itself. The cosmic beacons of permanence reveal themselves as fragile, hesitant, undecided. Humanity stares into the heavens and sees not answers but fractures, not endings but multiplicities. The scientific shock of stellar death is more than physics. It is philosophical rupture. If stars, the very anchors of the night sky, can split into two realities, then perhaps our own existence is also uncertain. Our reality only one among many. The cosmos is not a stage of certainties, but of probabilities. And in that revelation, the universe becomes stranger than myth ever dared to dream. The shock had broken the illusion of certainty. What once seemed simple, the collapse of a massive star into either neutron star or black hole, was now revealed as ambiguous, fragile, unresolved. To move beyond shock, scientists turned to their most powerful instruments, peeling away layer after layer of mystery. What they found was not resolution, but a deeper abyss. The first tool was light. For centuries, astronomers relied upon photons, tracing their journeys across space to tell the stories of stars. In the 20th and 21st centuries, this light was dissected with surgical precision by X-ray telescopes like Chandra and XMM-Newton, which probed the faint emissions of neutron stars. These compact remnants revealed themselves as objects of extremes. A single teaspoon of neutron star matter outweighed mountains. Their surfaces were crusts of atomic nuclei packed tighter than steel, while beneath them lay oceans of neutrons flowing like a quantum liquid. Yet even here, the boundary with black holes loomed. Neutron stars spun rapidly, their magnetic fields whipping beams of radiation into the void. Some, known as pulsars, blinked rhythmically as cosmic lighthouses. Others glowed faintly in X-rays, their heat the dying echo of collapse. Astronomers measured their masses and radii, trying to map the threshold of survival. A neutron star to massive would collapse, but the line was blurred. Could the densest neutron stars be hiding black holes within? Could some collapse teeter so precariously that their fate changed depending on imperceptible fluctuations? The investigation expanded with the NICA telescope aboard the International Space Station, designed to measure neutron stars with unprecedented precision. NICA revealed hotspots on their surfaces, distorted by extreme gravity. These measurements suggested that neutron stars were slightly larger than expected, adding tension to theories that sought to define their maximum mass. Each refinement of data pressed the question: how close can a neutron star come to being a black hole without crossing the threshold? Then came a new sense: gravity itself. In 2015, LIGO detected gravitational waves, the ripples in spacetime from colliding black holes. For the first time, the universe spoke in vibrations, not light. Soon, Virgo joined the effort, and a new era began. Suddenly, astronomers were not merely seeing stars, they were feeling the tremors of their deaths. These waves told stories light could not. They carried signatures of mergers, the masses of objects spiraling into one another. Some were clearly black holes. Others, like the 2017 event GW170817, revealed merging neutron stars. This event was unique. It produced both gravitational waves and electromagnetic light. A multi-messenger discovery that allowed scientists to watch collapse from two perspectives. The aftermath was even stranger. The merger created a remnant heavier than any stable neutron star should be, yet for a brief time it resisted collapse. The remnant spun rapidly, supported by angular momentum and magnetic fields, before finally collapsing into a black hole. The data suggested an object balanced at the knife edge between fates. For moments, the universe may have contained something neither fully neutron star nor black hole, but a liminal state between them. Supercomputer simulations added weight to this picture. Models of stellar collapse revealed chaotic interiors where turbulence, rotation, and neutrino fluxes altered the outcome. Tiny differences in initial conditions, the way mass was distributed. The spin of the star could determine whether collapse produced a neutron star or black hole. In some simulations, the same star under slightly different assumptions ended with different outcomes. Reality, it seemed, was less deterministic than imagined. This blurred boundary challenged not only astrophysics, but cosmology itself. If collapse could linger between states, could reality itself be unstable? Could quantum mechanics, usually confined to atoms, reach upward to sculpt the destiny of stars? Further evidence came from anomalies. In 2019, LIGO detected an object of 2.6 solar masses merging with a black hole. This mass was too heavy for any neutron star known, yet too light for typical black holes. It was the first confirmed inhabitant of the mass gap. Was it a heavy neutron star, a light black hole, or something entirely new, a transitional object? Astronomers debated, but the fact remained: nature had crossed into forbidden territory. Other events hinted at the same. Some pulsars appeared too massive to be explained by standard neutron star physics. The discovery of PSR J0740 plus 6620, a pulsar weighing about 2.1 solar masses, pushed theories to their breaking point. If neutron stars could be this heavy, how close could they come to collapse? Could some exist as black neutron stars, objects hovering just before the point of no return? perhaps with horizons forming and dissolving like flickers in space-time. Investigations widened beyond electromagnetic and gravitational signals. Neutrinos, ghostly particles barely interacting with matter, offered another path. When a star collapses, vast numbers of neutrinos are released, carrying away most of the energy. In 1987, neutrino detectors captured a handful of particles from supernova 1987A, confirming theories of collapse. Since then, detectors have multiplied, waiting for the next galactic supernova. When it arrives, neutrinos may reveal the moment a star hesitates between neutron star and black hole, exposing the delicate balance. All the while, theorists probed with mathematics. General relativity's equations described smooth collapse into singularities, yet they failed at quantum scales. Quantum mechanics predicted resistance, yet offered no clear mechanism. In this conflict, new theories emerged: quark stars, strange stars, exotic matter composed of particles beyond neutrons. Perhaps these exist between neutron stars and black holes, occupying the forbidden mass gap. They could be stars whose cores dissolved into quark soup, denser than neutron stars but not collapsed into black holes. If such objects exist, then the binary choice of fates is an illusion. There is not one destiny, but many. Even the cosmic microwave background whispered hints. Tiny fluctuations in its ancient light suggested that quantum fluctuations shaped the structure of galaxies. If quantum physics sculpted the birth of the cosmos, could it not also sculpt its deaths in stars? The unity of beginning and ending, bound by uncertainty, grew harder to ignore, and still, the voyages of data pressed outward. Astronomers analyzed fast radio bursts, mysterious millisecond-long blasts of radio waves from distant galaxies. Some theories tied them to collapsing neutron stars, straddling the threshold before black holes. Each burst might be a final cry of a star splitting realities, a last flare before silence. Step by step, the deeper investigation revealed not clarity but complexity. Every new tool from NICE's X-rays to LIGO's gravitational waves, from neutrino detectors to supercomputer simulations, widened the picture, showing collapse as unstable, turbulent, and perhaps quantum in essence. The story was no longer about one star or one fate. It was about thresholds, liminal zones, where reality itself hesitated. The deeper science looked, the more the universe resembled a mirror of uncertainty. Perhaps, some whispered, this is the lesson, that stars are not merely masses of plasma burning through fuel, but laboratories of being, stages where the laws of physics test themselves against the abyss. That in their depths we glimpse not only astrophysics, but the structure of reality itself. The investigation continues. But the haunting truth is clear. At the edge of collapse, stars reveal that reality is not singular, but fragile. And in their deaths, they may split not only into remnants, but into two realities at once. The deeper the investigation went, the more the cosmos revealed its unease. The universe, once thought to obey clear rules of stellar destiny, began to fracture into questions. What was supposed to be a straightforward sequence, a massive star either stabilizing as a neutron star or collapsing into a black hole, unraveled into a tapestry of contradictions. The line between fates blurred. The mystery did not dissolve with more data. It escalated. At the center of this escalation lay the mass gap. For decades, astronomers observed neutron stars up to around 2 solar masses, and black holes beginning at roughly 5. Between them stretched a desert, an absence of observed objects. It was assumed this desert was real, a natural boundary. Neutron stars could not grow beyond their limits without collapsing. Black holes could not exist below a certain mass because stellar collapse always delivered more. The gap seemed like an anchor of certainty. But then, the anchors broke. Gravitational wave observatories detected objects merging that defied these categories. In 2019, LIGO and Virgo reported an object of 2.6 solar masses colliding with a black hole. Too massive for a neutron star, too light for a black hole. Astronomers struggled to classify it. Was it a bloated neutron star, a featherweight black hole, or something new, born from a physics yet unseen? The once empty gap was now populated, not with clarity but with paradox. The uncertainty multiplied. Other detections suggested black holes lighter than expected, neutron stars heavier than predicted. The walls of the categories bent. Was there a continuum between neutron stars and black holes, with exotic states, of matter bridging the divide? Or were these detections signs of branching realities, where collapse resolved differently depending on probabilities deeper than physics could articulate? As data accumulated, the very fabric of collapse grew unstable. Theorists spoke of quantum gravity, the yet unwritten union of Einstein's relativity and quantum mechanics. In relativity, collapse is absolute. Once a star crosses the event horizon, no force can prevent singularity. In quantum physics, absolutes do not exist. Probabilities blur certainty, outcomes branch. At the intersection of these laws lies stellar death, and it is here, some suggest, that reality itself may fracture. Speculation arose around cosmic censorship, a principle proposed by Roger Penrose. It holds that singularities, the infinitely dense points predicted by relativity, must always be hidden behind event horizons, protected from the outside universe. Nature, in this view, censors her deepest secrets. Yet some collapse simulations suggested the opposite. Under certain conditions, collapse might expose naked singularities, points where space-time breaks open to infinity. To some, these were mathematical curiosities. To others, they were cracks in the cosmic mirror, places where different realities might emerge. Then came the anomalies in pulsar data. Observations suggested some neutron stars were spinning with such speed and carrying such mass that their very existence strained known physics. If they were stable, it meant neutron matter could resist gravity longer than believed. If they were unstable, then their survival meant we were observing them mid-transition, caught between being neutron stars and collapsing into black holes. Perhaps they were both, depending on perspective, the cosmos itself unable to decide. The mystery deepened further with fast radio bursts. These brief explosions of radio waves, lasting mere milliseconds, originated in distant galaxies. Their power was immense. In that instant, some outshone entire galaxies. Many linked them to magnetars, hypermagnetic neutron stars. Yet some bursts repeated, while others seemed like final cries. Speculation grew. Could these bursts be the last signal of neutron stars collapsing into black holes? The threshold broadcast across the cosmos. If so, each burst might be a beacon. From a star splitting into dual realities, one where it collapses, one where it resists. Escalation also came from gravitational wave patterns. Some signals hinted at remnants that oscillated in ways not fully consistent with black holes or neutron stars. Were these transitional objects? Or were we catching reality in the act of branching, the merger producing two outcomes, each rippling through space-time? To an observer in our universe, only one result appeared. But in another branch, another story unfolded. The philosophical unease grew alongside the science. For centuries, stars were symbols of constancy. Navigators trusted them, poets exalted them, civilizations aligned monuments to their rising and setting. Stars were permanence. Now they revealed themselves as uncertainty. Their fates were not fixed, but precarious, written in probabilities rather than absolutes. The cosmos, once imagined as a theatre of order, appeared instead as a stage of indeterminacy. This unease extended to humanity's place in the story. If stars could straddle realities, could humans as well? If the universe split at the deaths of stars, did it not also split in the choices of beings? Every stellar collapse became a metaphor, perhaps even a mirror. We, too, hover at thresholds, our lives unfolding in branches unseen. Yet escalation was not only philosophical, it was technical, urgent. The Voyager probes, now drifting in interstellar space, continued to measure cosmic rays, particles born in violent events like supernova. Their data hinted at distributions that did not align neatly with expectations. Were some of these particles birthed from exotic collapse events, neither neutron star nor black hole, but something between? The possibility lingered like a question carried on the solar wind. Meanwhile, supercomputer simulations painted collapse as chaos. Models of massive stars revealed that turbulence inside their cores was decisive. Tiny fluctuations, a wave here, a magnetic twist there, altered the outcome. Collapse was not a smooth descent, but a storm, sensitive to quantum-scale randomness. If the same star could collapse differently under near-identical conditions, then fate itself might not be singular. This led to a terrifying possibility. What if collapse was not deterministic at all, but fundamentally probabilistic? What if a single star, at death, split into two realities, one birthing a black hole, the other leaving behind a neutron star? To us, only one branch is visible, but the universe, vast beyond comprehension, may carry all outcomes. Each stellar death would not simply end a life, but fracture existence. The escalation reached its emotional peak in the awareness of limitation. The Voyager's instruments fade. LIGO's range, though vast, is finite. Nysa and Chandra will one day fall silent. Our tools are limited. Our glimpses of the abyss, fragmentary. We stand at the edge of cosmic truth with imperfect eyes, and the stars, in their depths, may be writing truths we cannot fully read. The haunting weight of this realization is inescapable. The most luminous symbols of permanence are now symbols of uncertainty. Stars, which once anchored myths and guided ships, now suggest that even reality may be unstable, fractured, branching. The mystery deepens, not toward resolution, but toward revelation. The universe is not a singular story, but perhaps a chorus of overlapping fates. Every star may be both neutron star and black hole. Every collapse, both silence and survival. Every death, a split in reality itself. When science meets paradox, speculation blooms. The deaths of stars balance precariously between black holes and neutron stars. Between certainty and probability, force physics to confront its own incompleteness. The cosmos does not hand us clean answers. It hands us contradictions. To navigate these contradictions, scientists construct theories, scaffolds rising into the unknown. Some are precise, grounded in mathematics. Others reach toward philosophy. All attempt to illuminate what happens when a star teeters at the edge of two realities. The first and most familiar speculation is the multiverse. Rooted in quantum mechanics' many worlds interpretation, it suggests that every quantum event splits reality into branches. If this holds not only for electrons and photons, but for stars and galaxies, then stellar collapse becomes one of the grandest branching points of all. A massive star dying at its limit may split the universe. In one branch, its core stabilizes as a neutron star. In another, it plunges into the abyss of a black hole. Both fates exist, but in separate, parallel universes. To us, only one is visible. To the totality of existence, both are true. Each star, then, becomes a cosmic doorway, creating new realities as easily as it sheds light. From this perspective, our universe itself might be the offspring of such a fracture. Perhaps a star, collapsing in another cosmos, gave birth to ours. The black hole that formed in its reality may be the Big Bang in ours, the singularity re-emerging as creation. The multiverse transforms stellar death into cosmic genesis. Every ending births beginnings. Every fracture is fertile. A second speculation arises from quantum tunneling, a phenomenon observed at the smallest scales. In quantum physics, particles can slip through barriers that classical physics deems impenetrable. If such tunneling applies at stellar scales, then collapse itself may be a star might tunnel between fates, choosing neutron star or black hole depending not on inevitability, but on chance. From the outside, we see one result, but in the mathematics of probability, both outcomes exist. Collapse is no longer an executioner's blade, but a dice throw across the fabric of space-time. Linked to this is the speculation of exotic states of matter. Neutron stars themselves are exotic objects where matter is crushed into a density beyond imagination. A teaspoon weighing billions of tons. Yet theories predict even stranger possibilities. Quark stars, where neutrons themselves break apart into their quark constituents. Strange stars, composed of strange quarks forming a new, stable matter. These hypothetical objects could exist in the very mass range that confuses us between neutron stars and black holes. Perhaps the gap is not a mystery of missing objects, but of undiscovered states of being. What we call uncertainty may instead be variety. Then comes loop quantum gravity and string theory, two great frameworks vying to describe quantum gravity. In loop quantum gravity, space-time itself is discrete, woven from indivisible loops. Singularities, points of infinite density, cannot exist, for space cannot compress beyond its smallest unit. In this view, collapse halts before singularity, producing either a bounce or an exotic remnant. Stars may collapse into black holes that eventually rebound, birthing new universes. In string theory, the story is richer still. The fabric of the universe is not points, but vibrating strings, and the vacuum itself holds landscapes of possible states. Collapse, in this picture, may not end in one outcome, but in many, depending on which configuration the strings assume. Each star, then, is not merely a body of plasma and fusion, it is a laboratory where the deepest structures of existence are tested. Philosophical reflection intertwines with these ideas. If every black hole births a new universe, then perhaps our own cosmos is a lineage of stellar deaths. Each universe inherits laws slightly altered, a cosmic natural selection. Those universes whose laws permit stars, galaxies, and complexity endure. Those without them fade into silence. Stars thus become seeds not only of planets and life, but of universes themselves. Every twinkle in the night sky may conceal the possibility of infinite progeny. Yet another speculation emerges from the holographic principle, rooted in black hole thermodynamics. It suggests that the information within a region of space can be described by data encoded on its boundary. A black hole's entropy, for example, is proportional not to its volume, but to its surface area. If this principle holds universally, then our reality may itself be a projection, a hologram encoded on a distant boundary. Stellar collapse, in this context, might not split realities, but reveal that reality was never singular to begin with. When a star collapses, what changes may not be the star itself, but the way its information is written on the cosmic ledger. One surface may encode it as a neutron star, another as a black hole. Both encodings exist, and in some sense, both are real. Beyond the mathematics, speculation becomes metaphor. Nietzsche once spoke of eternal recurrence, the idea that the universe endlessly repeats. Roger Penrose proposed conformal cyclic cosmology, where the infinite expansion of one cosmos becomes the seed of another. In both visions, endings contain beginnings, and death is never final. The split star, balance between fates, becomes a symbol of recurrence itself, an echo of the eternal dance between destruction and renewal. Speculation also turns to information itself. Hawking's black hole paradox revealed that information falling into a black hole seemed to vanish forever, violating quantum theory. Later, insights suggested that information might be preserved in subtle correlations encoded in Hawking radiation. If so, then even the collapse of a star into a black hole does not erase its story. It transforms it. In one reality, the story continues as a pulsar, sending signals across space. In another, it is encrypted in the horizon of a black hole. Both are narratives preserved, one readable, one hidden. More radical still is the idea that the laws of physics themselves are probabilistic. Not just events, not just particles, but the very constants of nature may shift between outcomes. In this view, when a star collapses, it may not only split into neutron star or black hole, but also alter the values of fundamental constants in the realities that emerge. Gravity may be stronger in one branch, weaker in another. Electrons may weigh slightly more, or protons less. Entirely different universes may blossom from a single stellar death. The star, in dying, becomes a shaper of worlds. As these speculations accumulate, the line between science and philosophy blurs. Yet this blurring is not weakness. It is recognition. For at the edge of knowledge, theory must stretch toward poetry. To contemplate stars splitting into dual realities is not merely to do physics, but to meditate on existence. The weight of these ideas presses back on human life. If stars fracture reality, then perhaps we, too, exist in branches. Every choice may echo like collapse, creating paths unseen. Each life could be as multiplicative as stellar death, branching into versions that love, versions that lose, versions that vanish. We see only one. The others, like alternate fates of stars, remain hidden. The speculative horizon stretches far. Perhaps there are universes where no black holes exist at all, only neutron stars. Others where collapse always proceeds to singularity. Still others where every death is a bounce, and the cosmos resounds with endless rebirth. In contemplating the split of a single star, we glimpse an infinity of possibilities. Yet speculation, however vast, must circle back to mystery. For all the theories, multiverse, tunneling, exotic matter, quantum gravity, holography, none has been proven. Each is a reflection in the mirror of the unknown, a possible face of truth. The star that split into two realities remains elusive. We stand at its threshold, armed with equations and metaphors, aware that certainty may forever recede, and so the theories remain, not as answers but as possibilities. They are scaffolds of imagination, built in the hope of touching reality's fabric. They reveal that physics is not merely about matter and energy, but about possibility itself. Stars, in their depths, are not just celestial phenomena. They are mirrors held to existence, reflecting multiplicity, uncertainty, and the haunting beauty of realities that might be. The star that split into two realities is thus not just a question for science. It is a question for being. What does it mean if the universe itself is never singular, but forever branching? What does it mean if every star is both flame and abyss, both survival and silence, both this and that, depending on the path unseen? The story of the star that splits into two realities is not confined to imagination. It is not locked forever in the vaults of speculation. Humanity, with fragile hands and finite lifespans, has built instruments to listen to the dying of stars, to catch the faintest tremors as they collapse, to test whether fate is singular or plural. These instruments are the lanterns of science, cast into a darkness that dwarfs us. And though their beams are narrow, they reveal glimpses of the most profound mystery we have ever faced. Whether reality itself divides at the threshold of stellar death, the first of these instruments is LIGO, the laser, Interferometer Gravitational Wave Observatory. In 2015, its twin detectors in Louisiana and Washington captured ripples in space-time itself, waves born from the merging of two black holes over 1 billion light-years away. It was the first time the universe was heard rather than seen. Since then, LIGO, along with its partners Virgo in Italy and Kagra in Japan, has detected dozens of mergers, black holes colliding, neutron stars spiraling together, sometimes ambiguous objects hovering between categories. These observations are crucial. They probe the mass gap, that strange desert between the heaviest neutron stars and the lightest black holes. Each new signal is a clue, perhaps even evidence, of stars that do not choose one fate cleanly, but hover at the edge, blurring categories, challenging the singularity of outcomes. The future will expand this listening. LISA, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will unfurl its detectors across millions of kilometers in space. It will sense the slow, deep rumble of massive black holes and extreme events far beyond LIGO's reach. If stars do split realities, if collapse teeters at thresholds unknown, gravitational waves may carry their fingerprints. But gravity is only one messenger. Light, in its many wavelengths, tells another story. The NISA mission, mounted on the International Space Station, peers into neutron stars with exquisite precision. By measuring the X-ray pulses from rotating neutron stars, NISA has already constrained their radii and masses to new levels of accuracy. In doing so, it maps the edges of stability, the line where neutron stars may cease to exist and collapse into black holes. These measurements help determine whether exotic stars, quark stars, or strange stars might exist in between. If NISA finds a neutron star heavier than theory predicts, it would signal a fracture in understanding, perhaps a sign that collapse does not lead to a single path above NISA's orbit. The James Webb Space Telescope extends humanity's gaze into the remnants of supernova, the violent deaths of massive stars. Webb's infrared eyes can peer through dust to examine collapsing cores, to measure the turbulence and energy of the final moments. Its observations of supernova-like curves and remnants help refine models of collapse. And in those models lies the question: does collapse end cleanly, or can it branch? Does the violence hide multiplicity within its brilliance? The Square Kilometre Array, SKA, under construction in South Africa and Australia, will transform the study of pulsars, rapidly spinning neutron stars whose beams sweep across Earth with unprecedented sensitivity. SKA will catalogue tens of thousands of pulsars, including those in binaries where mass transfer may push them toward collapse. Some may teeter at the edge of transformation, observing their timing, irregularities, and sudden glitches may reveal the delicate balance between stability and implosion. And in that balance, again, lies the question of dual fates. Other instruments extend beyond light and gravity. Cosmic ray detectors on Earth and in orbit search for high-energy particles born in if exotic stars exist, or if collapse sometimes produces unusual outcomes, their signatures may appear in these cosmic rays. The Pierre Auger Observatory in Argentina and satellites like AMESO to aboard the ISS track these particles, probing whether stellar death occasionally writes messages in charged particles, beneath mountains and deep in mines. Neutrino detectors like Super Kamio Kondi in Japan wait for the faintest whisper of a supernova. Neutrinos are the first messengers to escape a collapsing star, carrying information about the conditions inside its heart. In 1987, neutrinos from supernova 1987A reached Earth, confirming theories of stellar collapse. Future detections, with detectors like Dune under construction in the United States, may reveal whether collapse sometimes hesitates, splitting into different outcomes. A sudden change in neutrino flux could mark a star lingering between neutron star and black hole, perhaps for seconds, a liminal phase where realities might diverge. And then there are the supercomputers. No telescope or detector can enter the core of a collapsing star, but simulations can. With billions of calculations per second, they model the turbulence, the nuclear reactions, the neutrino flows, the magnetic fields. They show collapse not as a clean descent, but as chaos. Minute differences in rotation, in density, in magnetic field can alter the outcome. Some simulations end in neutron stars, others in black holes. Some hover on the threshold, unstable, flickering between fates. In that flicker, theorists see the possibility of dual realities, collapse balanced on a quantum edge. New missions are already being conceived. The proposed interstellar probe, envisioned to travel 10 times farther than Voyager, could one day carry instruments to detect interstellar black holes, to map the environments where stellar collapse has reshaped space. Future X-ray and gamma-ray telescopes may catch collapses in real time, watching the exact moment when a star crosses its threshold. Together, these instruments weave a net, fragile, partial, but growing stronger. Each strand catches a different messenger: light, gravity, neutrinos, particles. Together, they form multi-messenger astronomy, the science of listening to the universe with all senses at once. This convergence is essential. If stars truly split realities, the evidence may be subtle, encoded in correlations across messengers. A gravitational wave that hints at a too-light black hole. A neutrino burst that lingers too long, a light curve that dims too quickly. None alone prove multiplicity, but together they may whisper of it. The race is urgent, for the universe is vast, but opportunities are rare. Massive stars do not die often, at least not near us. Their deaths are fireworks spaced across centuries. To catch them, humanity must be vigilant, with eyes and ears open across the spectrum. And when one occurs, when light, gravity, neutrinos, and particles all arrive, it may be our best chance to see whether collapse is singular or split. Beyond instruments, there is ambition. Physicists dream of probing quantum gravity directly, of building detectors sensitive enough to see the very granularity of spacetime. They imagine quantum simulators, ultra-cold atom systems that mimic stellar collapse on a tabletop. They plan missions to orbit black holes, to map their horizons with precision, to test whether information is lost or encoded. These ambitions, though decades away, are the seeds of future answers, and yet, even with all these tools, the mystery may remain unresolved. Instruments may fail. Collapses may be too distant. Data may remain ambiguous. The voyages of science may drift into silence, as Voyager 1 does in interstellar space. Still, the pursuit itself carries meaning. To build LIGO, to launch Webb, to dig detectors deep underground, is to declare that humanity is willing to reach for answers even when certainty may never come. The tools of science are not only machines. They are also mirrors of humanity's longing. Each detector is a monument to the refusal to accept darkness without question. Each telescope is a declaration that mystery is not to be feared but approached. In this sense, the study of stars at the edge of collapse is also the study of ourselves at the edge of knowledge. The star that splits into two realities remains hidden, but its shadow falls across every dataset, every simulation, every theory. And in the quiet work of detectors and telescopes, the shadow may one day sharpen into form. Whether the answer proves multiplicity or singularity, the journey toward it is itself a triumph, proof that even a species bound to one planet can reach into the heart of stars. For now, the instruments listen. They wait for the next collapse, the next ripple, the next whisper. Somewhere, a star prepares to die. When it does, our tools will be ready, and perhaps, in its death, we will glimpse whether the cosmos is singular or forever branching. The star, once singular, now lingers in imagination as a fracture, a point where the fabric of reality itself may have torn, casting shadows of multiplicity across the infinite night. The journey through science has revealed its thresholds, its boundaries, its strange hesitations between collapse and endurance. And yet, when all instruments fall silent, when data pauses and equations end, what remains is reflection. What does it mean for humanity if a star can split into two realities? To answer, one must return to imagery, to the star itself. A burning sun, born in a cloud of dust and fire, living for millions of years, then collapsing under the weight of its own gravity. To the unaided eye, its light is steady, eternal, but to science, it is fragile, finite, poised between endings. One path leads to a neutron star, dense and pulsing, a beacon of order in the void. The other to a black hole, an abyss from which no light escapes. Two fates, mutually exclusive, yet both written in the mathematics of collapse. Here lies the tension. The cosmos demands one outcome, yet quantum whispers suggest that both may unfold. Reality may not be singular, but branching. And if stars can divide existence, then so too may every process, every particle, every choice. This vision touches human life with profound intimacy. For if reality can split, then each life may also exist in multiplicity. Every decision, every hesitation, every path taken or left behind may have unfolded somewhere. One reality where a voice was spoken, another where it was silenced. One where love endured, another where it was lost. To live, then, is to inhabit one branch of an infinite tree, a single melody among countless harmonies. Yet this does not diminish meaning. On the contrary, it deepens it. For the uniqueness of a life lies not in its exclusivity, but in its perspective. A single branch, though one among many, holds a view that no other does. To be conscious in one world is to carry the full weight of its singularity, even if others echo elsewhere. The dying of stars has always carried symbolic weight for humanity. Ancient cultures saw them as gods, as ancestors, as eternal fires in the sky. Their collapse into black holes or neutron stars does not lessen their symbolism. It magnifies it, for in their death they reveal truths about existence itself, that permanence is an illusion, that endings carry transformations, that reality is less stable than it appears. The star that splits into two realities is not merely a scientific hypothesis. It is a metaphor for uncertainty itself. Human beings seek certainty in science, in love, in belief. But the cosmos may be built upon uncertainty, not as error, but as foundation. If stars hesitate between fates, then uncertainty is not weakness, but the architecture of reality. There is fragility in this thought. If collapse can branch realities, then nothing is entirely predictable. The future may not be determined, but may scatter into multiplicities. And yet there is also resilience. For in branching lies possibility. The cosmos may not be a line, but a river delta flowing in countless directions. To exist at all is to participate in one flow, one current, one world among many. The golden age of physics, from Einstein to Hawking, has taught us to expect paradox. Relativity bent time, quantum mechanics shattered certainty, black holes challenged information itself. The idea of stars splitting realities is not so much an anomaly as it is the continuation of this pattern, the cosmos forever deeper than our first glance allows. What then is humanity's role? If the cosmos branches, if stars fracture reality, then human knowledge becomes both limited and infinite. Limited because we inhabit only one branch and cannot see the others. Infinite because the very act of questioning reaches beyond branches into the pattern itself. Science cannot collapse uncertainty, but it can illuminate it. Philosophy cannot answer definitively, but it can transform uncertainty into wonder. The emotional resonance of this mystery is profound, for it suggests that existence itself is not a fixed edifice, but a living tapestry. To look at the night sky is not to see stars fixed in certainty, but stars poised on thresholds, embodying the very ambiguity of being. Their deaths, like our lives, may not resolve into one answer, but into many. And yet, even if multiplicity is true, each world feels absolute. To the observer, there is only one sky, one earth, one life. This tension between multiplicity and singularity is the heart of meaning. To know that countless realities may exist, but to feel the weight of this one is to recognize both fragility and sanctity. Perhaps, in the end, the mystery is not whether stars split realities, but why the cosmos allows us to wonder about it. A species bound to one planet, orbiting one star, can look out and imagine infinities. This capacity to see multiplicity in a single light, to glimpse eternity in a flickering star, is itself the greatest triumph of consciousness. There is, however, a haunting possibility. If collapse can branch, then perhaps the universe itself was born from such a fracture, a star in another cosmos, collapsing into a black hole, its singularity giving birth to our space-time. If so, then we are the children of fracture, the echoes of multiplicity. Our entire universe may be but one branch of another's ending. This vision turns human fragility into grandeur. For if universes are born from branching, then every reality is both finite and eternal. Finite in its singular flow of time, eternal in the infinite branching that surrounds it. The star that split into two realities becomes, then, a parable of existence itself. It tells us that certainty is illusion, that reality is plural, that endings are beginnings in disguise. It tells us that even in collapse there is creation, that even in division there is multiplicity. And so, the final meditation returns to the image of the star, a singular point of light in the night sky, burning, collapsing, poised between fates. In one world, it becomes a neutron star, pulsing faintly, a reminder of endurance. In another, it becomes a black hole, swallowing light, a reminder of mystery. Both outcomes are real, each in its own world. And we, standing beneath the stars, are left to ask, in which branch do we live? The answer may never come. Instruments may listen, telescopes may watch, philosophers may reflect, yet certainty may remain beyond reach. But perhaps this is the truest reflection of the cosmos, not that it provides answers, but that it invites wonder, for to wonder is to live, to stand beneath a sky filled with stars, and to ask whether their depths fracture reality is to embrace both, science and philosophy, both reason and awe. It is to accept that existence is not only about knowing, but about marveling. Thus, the star that split into two realities is not only a scientific question, it is a mirror. In it we see our own multiplicity, our own uncertainty, our own fragility, and our own grandeur. When the star split, both realities endured. And so, perhaps, will we not in certainty, but in multiplicity, as echoes in the great symphony of existence.